the first example problem that we're going to work through in this chapter, we are told we have a cat chases a bear 7 meters up a tree. The bear, very scared of the cat, loses its grip and falls to the vicious cat below. So the questions are, how long does it take the bear to fall, and how fast is the bear moving when it hits the ground? So we drew a picture here. We talked about I like to have the height of ground level to be 0. There's no fundamental reason why I must choose ground level to be a height of 0, but in most cases, that is the most convenient thing for me to work with. It is intuitive for the way my mind works, so I want to have it. If I set ground level to be 0 and upward to be the positive direction, that immediately forces me to set the initial position of the bear to be 7 meters high. Now, that also means that the acceleration due to gravity will be negative 9.8. The acceleration due to gravity near the surface of the Earth is 9.8 in magnitude, and because we chose upward to be the positive direction, Earth pulls down, Earth will accelerate you down, the acceleration will be a negative number. When I say near the surface of the Earth, I mean within a few miles of the surface of the Earth, which accounts for many scenarios in everyday life. If you go to the top of Mount Everest, the acceleration due to gravity is a little bit less than this, but you got to move miles away from the surface of the Earth before this changes in any meaningful way. The other thing we said is the initial velocity of the bear we set to be 0. So how can we justify that? Well, to think about it, let's draw the velocity of the bear at different moments. Now we know before the bear lets go, well, at that point it's still holding on to the tree, so the bear can't be moving. So before the bear lets go, the velocity of the bear is 0. So before bear lets go, the velocity is going to be 0. What about after the bear lets go? Well, when the bear has let go, it will be maybe just over here. So at this point, it's going to be falling downward, and it will have some velocity downward. And let's choose the relative size of this arrow is directly related to the relative magnitude of the velocity. So a bigger arrow will indicate a larger velocity. Well, at this moment, the bear is moving this fast, but before the bear fell to here, there was a moment where the bear was here, and its velocity would be smaller. And before the bear fell here, the bear was over here, and its velocity was smaller still. And before the bear was at this position, it had fallen only a little bit, and its velocity was smaller still. And I could continue this line of reasoning indefinitely, and the split second after the bear lets go, we could just say its speed is approximately 0. It's kind of like saying, at this moment, the velocity of the bear is v equals -2. I'm negative because it's going downward, and 2, I'm just making up a number. Well, before here and here, it has to be v equals -1. And before, from here to here, there has to be a moment where its velocity is -0.5. And we could continue this reasoning. There has to be a moment after the bear let go where its velocity was -0.000 on and on 1. This is technically after the bear let go. You can't, if you think about a number line, you cannot travel from 0 to 1 without traveling through 1/2. You can't travel from 0 to -0.5 without traveling through this teeny tiny number. But this number is non-zero. This number must be after the bear had let go. So I could just say this is close enough to 0 that we'll just set the initial velocity of the bear to be 0 itself. Now, to continue this problem, let's look at these equations. Let's think about what the problem is asking for. We are asked, at what time does the bear land? Well, when the bear lands, it is at a height of 0, so that means it's at its final height. At what time is this going to occur? That's one of the things we're trying to find, so I don't know what it is. And we also do not know the final velocity of the bear, so I will also indicate v is equal to some unknown. Now in this problem, as I said before, I wrote these equations out. I wrote them with x's, but replacing x with y for my position is just cosmetic. I'm not really changing anything in terms of the math. So here are two unknowns. The first question, what do we want to know? We want to know time. So I could look at these three equations and I could ask myself, is there an equation here where I have a value for every term except time? So if you want, pause the video, go through every term. Do we know x final? Do we know x initial? Do we know v initial? Do we know t? Do we know all these stuff? Go through them, see if there's an equation where time is the only unknown. So the equation I want to use is this one. The first equation I will write as y final is equal to y initial, v naught t, 1/2 a t squared. My position I'm writing as y for height. That's just a cosmetic change. I'm not really changing anything meaningful in this question. So let's see, do I know the initial position? Yes, I do. Do I know the final position? Yes, I do. Do I know the initial velocity? Yes, I do. Do I know the acceleration? Yes, I do. The only unknowns here are time. So I could plug numbers in. Y final, we said is 0. Y initial, we said is 7. V initial, we said is 0. Multiply by our unknown, which is time, plus 1/2. Acceleration, negative 9.8. And then I have t squared. Now at this point, I just have to solve the math. So I have 0 is equal to 7. 0 times t gives me 0. 9.8 and 1/2 is 4.9, so that will be minus 4.9 t squared. And now I could bring the 4.9 to the other side, so I get 4.9 t squared is equal to 7. Divide both sides by 4.9. Okay, these cancel. I get t squared is equal to, I put 7 over 4.9 in a calculator. I will get some number that I did not write on the sheet immediately in front of me, so I'll just write it like this. And then when I have this t squared, I want to get t, so I take the square root of both sides. And when I do that, I get two solutions. I get t is equal to plus 1.2 or t is equal to negative 1.2. So two solutions. Which solution do I want to go with? Now I'm going to think about what we're doing and connect it to something in reality. So if the bear lets go at t equals 0, this solution indicates the bear will hit the ground at t equals 1.2 seconds. So it'll hit 1.2 seconds after it lets go. This solution indicates the bear hits the ground at negative 1.2 seconds. So this is like saying the bear hits the ground 1.2 seconds before it let go. Now mathematically, this solution is fine, but when I connect the math of what I'm doing to what's physically happening in a problem, I realize this answer is unphysical, so I'm just going to throw it away, and the bear will hit the ground 1.2 seconds later. So I'll put 1.2, I'll just get rid of the plus sign, 1.2, and seconds for the time the bear hits the ground. For the second part of this problem, we are asked at what speed is the bear moving when it hits the ground? So just like before, I am going to look at these three equations, I'm going to look at what I know, and I'm going to see if there's any of these equations where I know everything except the speed or velocity of the bear. So we now know that this time is 1.2 seconds. I have a new piece of information I have at my disposal. So I could look at Well, we already used this equation, so we probably don't want to use it again. If I look at these other two equations, it turns out I could use either. I could use this one, or I could use that one. I'm going to choose to use this one because it's shorter. So if I say V equals V naught plus AT, let's say V is what we're really trying to find. V naught, we said, is 0. Acceleration due to gravity is negative 9.8. And time is 1.2. So negative 9.8 times 1.2, I multiply those numbers together. I get V final is negative 11.76 meter per second. Now what I'm going to do is I'm going to think about what's really happening in this problem and what does the question ask for. The question asks how fast is the bear moving. So this is the final velocity. But the question is asking for final speed. A negative number indicates downward motion. A positive number indicates upward motion because velocity direction is important. And we chose upward to be the positive direction. So the negative number for my final velocity indicates the bear is falling. That's intuitively what we expect. You let go of the tree, you're going to move downward. So you are moving downward at 11.6 meters per second. So I could say the final speed, I could just write as 11.676 meter per second. And this is how fast the bear is moving when it hits the ground to fall victim to the vicious cat below. You could basically say speed is just the magnitude or the absolute value of velocity. In the next problem we're going to talk about, we have a car that starts at rest. It speeds up to 25 meters per second in 5 seconds. What is the car's acceleration? How far has the car traveled in those 5 seconds? So I'm going to keep these equations written right here just so they're right there for our reference. And the first thing I'm going to do is I'm going to draw a picture. So let's say here's our car. And it will begin right here, and then it will speed up, and later on it will be right here. And it's moving, so I'm going to give it those lines indicating motion. So the car starts at rest. Well, this is the initial moment. I'll just write initial here. This is the final moment. I'll write final here. If you start from rest, if you think about it, well, rest means you're not moving. That indicates your velocity is 0. So I could write here, V initial is going to be 0. It speeds up to 25 meters per second. Well, this is the final moment we're talking about. So when it gets here, it is moving at 25 meters per second. So I'm going to write V final is 25 meter per second. Now, I also want to set up a coordinate system. I'm allowed to set my coordinate system anywhere I want. There is no restriction on what I'm going to do, so do something convenient that's easy to work with. So I will choose to say here is the initial position is 0. This is only a choice. I am not required to do this, but this is a convenient choice to work with. And then the x-axis is going to point this way. So here's the positive x direction. At this point, the car is moving in the positive x direction at 25 meters per second, so the final velocity is going to be positive 25 meters per second. We are told also that this occurs 5 seconds later, so 5 seconds later, that means t is equal to 5 seconds. So of the 6 possible variables in these equations, we have X initial, X final, V initial, V final, A, and T. Which of these do we know right now? We set X initial to be 0. We do not know what X final is. We were told initially the car is not moving, and at the end the car is moving at 25 meters per second. We are told that occurs at a time of 5 seconds, and acceleration is currently an unknown. When I write these terms out, I don't like writing units because I think that clutters up my page, but if you want to do it, that's fine for you. So 0 meter, meter per second, 5 seconds, if you insist on writing units. I'd rather not do it. So at this point, I'm going to look for an equation that is easy to work with and tells me how far the car has traveled and what its acceleration is. Acceleration first, I look at these 3 equations. I notice the second equation. I know V final, I know V initial, I know T, I do not know A. So I could just right away plug numbers in. So I could say V final is equal to V initial plus AT. V final, 25, V initial 0, A is an unknown, T is 5 seconds. So 25 is equal to 5 times A. A is equal to 5 meter per second squared. Acceleration is measured in meters per second squared. The second part of this problem, how far has the car traveled? Well, now we have a new piece of information. So we could say this number is 5. It's just coincidence that the time is 5 seconds and the acceleration is 5 meters per second square. There's no fundamental reason why these numbers are identical. It just is a coincidence based on what was given in the problem. So how far has the car traveled? Really, either equation would work. So I'm going to choose to use this second equation here. If we want, we could use the first equation. The first equation might even be a bit easier, but it really does not matter. So we have V squared is equal to V initial squared plus 2A, X final minus X initial. V final square, 25 square. V initial squared, 0 squared, plus 2A, 2, acceleration is 5, X final minus X initial. X final is an unknown. X initial we set to be 0. So what I have is 625 is equal to 0 plus 10 x. So what I get is x is equal to 62.5. So after 5 seconds at this acceleration, the car has traveled 62.5 meters away.